All right, electric potential energy. Here we go. So this is going to be a lot of similarities here to what we did when we did gravitational potential energy, except of course there's a repulsion case, right? So to help visualize this, I want to get you to try and think about this and relate it to a physical experience and what you already know and so on, right? So I want you to really think about energy concepts as you try this little activity. Um, so if you could find a pair of magnets that you can use to attract or repel from one another, that'd be great. If you can't, I understand. I'll try and explain everything, and you can live vicariously through my description or other people's description of it. But anyways, so pretend like these are charged particles, right? So when you have a north and a north, that'd be like having two like charges. When you have a north and a south, that'd be like having two opposite charges. All right. So get that, please, if you can. Press pause or whatever. Go get it, and we'll go to the next stage once you press play and so on. Here we go. So the question is, play around with them and so on and investigate. So what would your answers be to when you push the two like charges together? So a north towards a north, when they're repelling each other, uh, do you have to do work? How much work? Does it get harder to push as the charges get closer or the magnets get closer? I'm just going to say charges the rest of the time. What does this mean with respect to the electric potential energy? You have to do work to move them. This was to go together, right? And then there's a follow-up question. You have to do work to move them further apart. Okay, so press pause and try it. Go through all these things, see what happens, right? So hopefully you've had a chance to try that and so on. If not, I'll kind of explain what happened here. So let me explain a little bit first, of course, right? When you have two charges that are repelling each other, obviously you have to like push to get them to go together, right? And yes, it gets harder to go together. The amount of work you're doing would just be like force times distance, except the force is changing as you go, right? So it's a little bit complicated, but you can certainly think of it as work done. And what does this mean to do with electric potential energy? Well, you're adding energy to that system, right? The further you push them together, the more energy that system has. When you let go, they'd fly apart with great amount of energy. Do you have to do work to move them apart? No, because if you let go, they'll just fly apart on their own. Magnets have this pesky habit of like flipping around and attracting to each other, but I mean, if they're forced to stay in the same rotation and you let go, they repel from each other, right? So these are those answers, right? So do you have to do work to push them together? Yes. How much work? Well, force times distance, right? Add it all up. And then does it get harder to push? Yes. You're increasing electric potential energy, and you have to do work to move them further apart. No, actually, the energy is automatically released, right? As they're pushed apart by the magnetic field that's meaning. Energy of the system is decreasing as they repel. It's getting transferred automatically to kinetic energy if you let them fly away from each other, if they would actually do that. All right, so that's the first one. The second part here, or third step, I guess, but the second thing you're doing with the magnets, other than getting the magnets, is what would happen if you're pushing the two opposite charges towards one another. You have to do work. How much work, I guess, as well, right? Does it get harder to push as the charges are getting closer together? What does this mean with respect to electric potential energy? So hopefully you're able to try it. And you're back now. And here's what you should find, right? So with that third step there, when you're pushing the two charges towards one another, do you have to do work? Well, no, the energy is automatically released as they attract together, right? Energy of the system decreases as they attract. It gets transferred to kinetic energy. Really, you're actually doing negative work on the system. You'd be holding against that magnetic force, right? So does it get harder to push them together as the charges get closer? No, actually, it gets harder to hold them apart, doesn't it? Kind of a weird situation. And so what does this mean with respect to electric potential energy? Is that as you are allowing them to get closer together, they're ending up, I'm going to come back to this one, I guess, because there's a graph to do with it in that. But yeah, it's the same as the gravity situation, right? You're allowing them to get a larger and larger negative value, and when the magnets are really far apart, they wouldn't have a force relative to one another, so there wouldn't be energy. So when they're really far apart, at infinity theoretically, there'd be zero energy. As they're coming together, energy is going out of the system into kinetic, right? So it's ending up with negative energy. Okay, so that's the answer there. I could just type that in, I suppose, but negative energy. Probably will add to that later on for the next time I use the file. But anyways, the description was verbal for a while there. So when working with two like charges, what way would you have to move the charges to give them potential to move closer together or further apart? There's two like charges, so north facing a north, or a positive and a positive, or south, south, minus, minus, right? Which way would you have to move them to give them some potential to move? Well, they're wanting to repel, right? So you have to move them closer together so that they would want to, or have room to fly apart, right? You have to push them together so they have room to repel apart. 5, when working with opposite charges, which way would you have to move the charges to give them room or potential to move, of course? And then that's the opposite, right? Where you'd have to, you need to pull them apart so then they can attract together, right? Pulling them apart adds energy to the system. And what happens when the charges get really far apart? Do they have potential then? Does it make a difference if you're dealing with like or opposite charges? If you have an attraction or repulsion situation, actually I should have said repulsion or attraction situation for the parallel structure, right? Like or opposite charges. In other words, repulsion situations or attraction situations. This should lead you to the same conclusions as with gravitational potential energy. Go to the next slide here and show but when they're really far apart, right, the electric force reduces to 0, and this means that there is no force on them, and so they don't have potential energy, right? If you don't have a force on you, you don't have energy. This is the case for both attraction and repulsion, right? So the same conclusion would be about the idea of it being 0 at infinity. Okay, so hopefully that gives you a good feel for what we're talking about here, and then everything we say here is easier as a result. So the energy stored if there's an electric field. Yeah, there's energy stored if there's an electric field, since there's an electric force, right? The force can be work, and so energy can be released, right? Work can be done. So the activity on the previous page, if you're thinking about it, if you're bringing two like charges together against the mutual force of repulsion, it takes work to do that. Work done and bringing them together stores energy in the system, and so in other words, it's adding energy. And so this is the very much easier to understand graph, right? As you're pushing them together, you get more and more energy stored. The arrow would be kind of like going that way, right? The weirder one down here, okay, is this discussion like we've already had with opposite charges. Instead, it's the pulling of charges apart against the mutual force of attraction that takes work, right? Bringing them together actually allows energy to release. And it releases from the system, becomes kinetic, and so it takes away energy from the system. So, and it takes energy to move the particle to an infinite distance away where it would have a 0 energy, right? And so 0 energy because there'd be no force, right? And so really it must have a negative energy. This is this, right? So it's a negative energy. There we go. Okay, and the closer they get, the more negative energy they have, right? And yeah, and then this is exactly the same as that gravitational potential energy situation that we've seen before. Okay, so it's just you have these two cases, so it just really makes it more complicated to kind of think through it. I had to really be careful planning this lesson and think it through. The blue curve, of course, as a recap analysis here. The blue curve represents the electric potential energy stored in the system when between two like charges when you have a repulsion situation. As their centers is increased, centers are increased. How far apart they are is increased. So notice this energy is always positive, and positive, remember, is a repulsive force, right? And the more electric potential energy, more electric potential energy is stored by moving the charges closer together, right? Bring them together, you get more energy stored. So the more you go this way, closer together, the distance between them is smaller, you get more energy. Okay. The red one, the red curve represents the electric potential energy in a two opposite charge system. So when you have attraction, notice that the energy is always negative. And given that the energy gets less and less negative as the distances become bigger, right? As they go apart, it becomes less and less negative energy, right? That is showing that you're storing, potential energy is stored by moving them farther apart. Okay? And so that's basically the same as with mass. If you lift something up, you're storing energy, right? So same with charges like this. End of the day bell. So notice that for both curves, as R becomes very large, both energies approach zero. Although for one situation, of course, the zero is a minimum level, and the other, it's a maximum level of energy. Kind of a weird thought that zero can be a maximum. So electric potential energy and the equation for it, this is going to be the same analysis as we did in the gravity one. This page is from the initial, the original ministry course that was provided for this 4U course. And so they don't sort of show as clearly there that this is kind of pretend math here because it's complicated because the forces are changing. But they're saying like, oh, same as before, like work equals force times distance, and we know the electric force times the distance then would give you the energy. But really, it's more complicated. You have to do like a geometric average. You have to do some integral calculus, but it does work out to be this nice simple result. Like the r's just cancel out, right? So we have that same idea as the gravitational potential energy equation. Instead of GMM over r, it's KQQ over r. Right, where the force version was r squared in each. Now we've got the just r version, and our sign stuff is new too, right? We have to account for a positive case and a negative case, right? If we have an opposite charges, that's an attraction situation, so it'd be a negative energy, and for like charges, you'd have a positive, two negatives or two positives, make a positive result. So positive energy means repulsion, right? So that's the new part there. We have this repulsion case where it was always just negative for gravity. And remember, energy is not a vector quantity, but they do have positive and negatives, right? So, yeah, same as we did with gravity, right? So pretty straightforward. You just basically the exact same calculations as with gravity, but you're talking about amounts of charge instead of amount of mass. So we have our given information. We metric prefixes here. If you're unfamiliar with some of them, go and Google it even. But I mean, like what this little U symbol is, you might not realize it's micro, right? So there is a page 774 in the virtual text. It's on the website or on our online course site, whatever you want to call it. Page 774, or you can just Google metric prefixes. It'll show you there's nano and there's pico and there's micro and so on. Okay, nano's -9, pico's -14. You got to know those after working with them a lot. Anyway, so these are just very small amounts of charge. Charge is an incredibly electromagnetic force is an incredibly strong thing, incredibly strong force, way stronger than gravity, right? So you talk about 2 or 3 grams or kilograms of mass, whereas you're never talking about 2 or 3 coulombs of charge. That's just a phenomenal amount of charge. It would be incredible amounts of forces. So our analysis, we're just going to use our energy equation, and we're going to plug the numbers in, and we're going to calculate. And I've done enough for those calculations, I think. I can trust that you can just use your calculator properly with your 10 to the -6 for the micro and so on. Okay, make sure you can get an 18 joules. If not, ask for help, and I will help you some more with it in a help post. Okay, that 18 joules, notice it's positive, right? Well, we had 2 negative charges. That's a repulsion situation, so it's positive energy, right? There we go. All that good stuff, right? So that's a repulsion situation. Energy was stored in the system in a positive way, like as you were pushing on them to get them to go together to that location. The other thing we want to talk about is like work done when moving a charge, right? And so if a charge is moved relative to another, it's being moved in an electric field, right? And so you can talk about the amount of work done, right, to change the amount of electric potential energy. So this is the kind of situation, you've got 2 charges and you're moving one relative to the other, and they're asking like how much work was done, right? To determine the amount of work done. So the main concept, of course, is just work done's final energy amount, take away the initial energy amount, right? Just like before, delta E, right? So you just, again, 2 calculations just like on the previous page, and you subtract them and so on. It's a little weird sometimes because one will be positive and one will be negative, and you just have to be careful and let the numbers do the work. And in this case, you'll see that we have a negative number. And so if you're looking at the situation, we have a negative, we have a repulsion situation. When we're moving it out, we're actually letting, when we're letting out, we're letting energy release from a repulsion situation, right? This is not a gravity-like one. This is different than gravity, right? So the negative means it's a repulsion situation, right? So energy was allowed to go out of the system. Think of when you're removing this, when you're grabbing the charge and moving it out. It actually wants to go out, right? You'd have to hold against it, like with the magnet when you were trying to bring um, the say the repulsion situation, and if you're moving it out, moving the magnets apart, you're actually holding inward as you allow it to move out, right? So you'd have a negative force because the force would be in the opposite direction of the distance. And I did that backwards. Actually, it should be a negative here, shouldn't it? So fix that up. Your force would be in the opposite direction of that displacement, right? So what's the last part here? Here, let me delete. If they ask for work done to move charge to an infinite distance, really that's just the same as asking for electric potential energy, right? So this could have been worded as how much work was done in moving it from an infinite distance to 2 centimeters, right? So just so you're aware of that. And then the complication of two-dimensional, and could even be, of course, in next level three-dimensional stuff. So electric potential energy is stored in a system of charges, right? And so positive and negative values, of course, combine, kind of like vectorially, but they combine algebraically, let's say, or like integer values would, negatives and positives, right? So we want you to calculate the total energy of this group of charges. Okay. So the first thing you should recognize is, in order to get, say, the electric potential energy between Q1 and Q3, you're going to need that diagonal length, right? And so you're going to need to do some dimensional or math for lengths. So the Pythagorean theorem needs to be used to get that length between them. It ends up being 2.24. And then what else? We're going to add up all those individual values. So we need all the different combinations of pairs of charges. So what are the different combinations of pairs of charges? You'd have like Q1, Q2 as a pair. You'd have Q1, Q3 as a pair. You'd have Q3, Q2 as a pair. And I think that's it. Because if you said Q3, Q1 is a pair, that's redundant. Q1, Q2, Q1 is redundant, and so on, right? So this different combinations of pairs of charges. If you've done the data management course, that's like number of possible combinations. That should seem like a familiar question, right? And so in this case, you have 3 things and you're choosing pairs of 2. So that's called 3 choose 2, right? The number of possible ways you can choose 2 unique pairs of 2 from a set of 3. Right. And so, if you're good with that, great, go for it. If not, Google's your friend. You could literally just type in 3 choose 2 and it'll show you that there's 3 pairs. That's not as helpful as the next step. Better yet would be, ask Google, what are the possible pairs of 2 of the numbers, of the 3 numbers 1, 2, 3. And it shows you like 1 and 2, 1 and 3, and 2 and 3. Right. So it actually gives those pairs. You can scale that up to 4 or 5 or 6 charges too, right? And it becomes way more complicated, obviously, right? So if we had 1, 2, 3, 4 or A, B, C, D, right? What are the unique pairs that you can have between 4 things? There's actually 6 of them, right? So 4 choose 2 mathematically in the data management course is 6. There's your 6 unique combinations, right? So there's all your possible pairs, and you would calculate the energy, potential energy from each of those pairs, and you'd add them all up. Some to be positive, some to be negative. You'd add them all up and you get your total. Okay. So with that in mind here, then we should be good with us having these different pairs, right? So we've got 1 and 2, and 1 and 3, and 2 and 3, right? This one, the 1 and 2, you'll notice is a repulsion situation. So that's a positive energy, I think, right? And these two, the other two, Q1, Q3, is an attraction situation, so it's going to be negative, and Q3, Q2 is an attraction situation, so it's going to be negative. So you would get values for these things, and you don't even have to think about the whether it's positive or negative, because it's going to end up working out with the way the signs work out. But it's obviously good to understand why it's positive or negative, right? And see that connection. Please do not put in here, right there and there. You're adding up all these energies. These blue things are adding up all the energies, right? Don't think of it as like, oh, we're going to subtract because it's a negative, because you'll end up with this being a negative, and then you're subtracting a negative, and you'll end up with a double negative by accident, and you'll get it wrong, right? So don't do that. Just let the math carry out, like I said previously here, and you should get your values. So this works out to be as we knew it would be, a positive adding to a negative and adding to another negative. So essentially it becomes subtract, of course. We end up with this result of negative 6.62. And so you can see that overall, this negative means that it's an attractive system, right? Overall, you can tell this is an attractive system because of it. Just basically, I guess, because the these two here, these are the bigger charges, and they're close to each other. So overall, this is an attractive system. They would attract together and blah, blah, blah. So that is it for this lesson, I think. Yeah, there we go. There's your practice assignment. And as always, thanks for watching. Let me know if you need any help. Post some post-help questions or email me, all that good stuff. So yeah, thanks for watching. And like and subscribe. And the more we can get this channel shared around, the more people get physics help, right? So like and share and subscribe. Tell your friends, whatever. Okay, Mr. Horn out.